Welcome to this explainer. Today we're diving into a really fascinating developer journey documented by a programmer named Ang. We're going to unpack the hidden and honestly pretty surprising nuances of Haskell error handling. If you've ever felt like your code was playing mind games with you, well, you are in excellent company today.
Let's start things off with a mystery, fueled by a question that seems completely obvious but actually hides a massive plot twist. Think about it. If you're working in Haskell and you pull in a monad transformer, literally called ExceptT, your brain immediately makes a connection, right? Except stands for exceptions, so naturally, this tool must catch my runtime exceptions. Well, hold on to your T-boards, because the actual answer is going to completely change how you look at your code.
To understand the original crime scene, let's look at Section 1, the staircase of case.
Ang initially brought the ExceptT wrapper into the codebase for a very specific and very relatable reason, to clean up that notoriously messy code pattern we call the staircase of case. You know the one, right? Where you have these deeply nested case statements checking for errors at every single step, and it just shifts your code further and further to the right of your screen. So Ang used ExceptT to flatten all that out, taking advantage of a brilliant early exit mechanism to keep the application flow nice and linear. To give you a sense of how this builds a beautiful pipeline, the sequence Ang set up for their X2 to ebook application is super straightforward. Step 1 is parse input. Step 2 is parse. Step 3 is convert to ebook. Because it's all wrapped up in ExceptT, if parse input fails, like say the input is invalid, the execution just short-circuits at the very first throw error. It instantly skips the rest of the steps. No nested cases, just a clean, elegant pipeline.
But, as it turns out, this beautiful pipeline sets a dangerous trap. Which brings us to Section 2, the ExceptT misconception.
Now what's really interesting here is the explicit promise of typed errors. When you define your stack as ExceptT app error IO, you are effectively making a contract. You're saying, hey, I will either return a successful IO operation or I will explicitly fail with an app error. It makes it seem like this wrapper is going to safely encapsulate our I/O operations in this perfectly typed little bubble. And this is exactly where the trap springs. Because the word accept is literally right there in the name, developers naturally harbor this misconception that the wrapper handles true system-level runtime failures. We just expect that if an I/O exception happens, or a file fails to read, ExceptT will swoop in, catch that system explosion, and politely hand us back a nice, clean app error. It's a totally logical expectation. I mean, it's based entirely on the name of the tool.
But as we all know, logic and programming don't always hold hands. Section 3, permission denied.
To test this exact assumption, Ang decides to simulate a real-world system failure by setting up a brilliant little trap in the terminal. First, they create a dummy file using touch/temp/foobar.txt. Second, and this is the vital part, they deliberately remove all read permissions from it using chmod a-r. Then, for step 3, they run their XS2 ebook console app directly against this totally unreadable file just to see exactly what XST is going to do. And boom! This brilliantly illustrates the sudden plot twist in Ang's developer journal. Instead of a clean, typed error safely caught by our trusty wrapper, the application brutally crashes with a raw stack trace. The terminal just spits out, open binary file permission denied. The ExceptT wrapper did absolutely nothing to stop the crash. It completely bypassed the safety net.
So Ang puts on the detective hat and starts digging into the parse input code to figure out why the safety net failed. They notice that on line 37, a function called doesFileExist smoothly converts its types using lift.io, bumping IO bool up to accept app error IO bool. And hey, that part works perfectly. But down on line 42, the code calls readFile on our unreadable foobar file. This triggers a true system-level IO exception, a massive explosion that the ExceptT wrapper simply could not contain.
This specific failure leads to the absolute most important realization of the whole explainer. Section 4, return values versus exceptions. Here is the crucial point, the ultimate aha moment. There is a stark contrast between these two concepts. ExceptT handles explicit return values. These are the errors you create manually in your own code using throw error or left. It handles those flawlessly. But true runtime exceptions, those are triggered by system errors, like the operating system flat out saying permission denied when you try to read a file. Those system-level exceptions bypass the ExceptT monad completely. It finally dawned on Ang. And honestly, this is a profound, fundamental lesson for all of us working in Haskell. ExceptT cannot handle runtime exceptions, it only handles return values.
Despite its incredibly deceiving name, it is strictly about managing control flow through return values, not about catching system panics.
So, now that we know the true identity of our tools, how do we fix it? Section 5. True runtime resolution.
This leaves us asking a pretty vital follow-up question. If our brilliantly named, yet ultimately deceiving wrapper doesn't actually catch true I/O exceptions, well, what tools actually do the job? How do we stop our Haskell apps from crashing when the file system throws a tantrum?
The answer, of course, lies in using the right tools for the right job. To handle true runtime I/O exceptions in Haskell, you have to use the dedicated exception mechanisms explicitly built for that task. Specifically, try, catch, and throw I/O. These are the actual functions that talk to the runtime system and can properly intercept those raw permission-denied explosions before they take down your entire application.
Aang wraps up this incredible first-hand journal entry with the perfect thought, writing, "Isn't this fascinating discovery?" And it really is. It proves that even a frustrating crashing application can lead to one of those truly insightful days of learning that just leaves you hungry for more. It really makes you wonder, though, if we can't trust a tool literally named ExceptT to handle exceptions, how many other naming conventions in our codebases are hiding massive architectural secrets just waiting to be uncovered? Keep questioning your tools, and I'll see you in the next explainer.